Hi there, this is Jude Socrates. Welcome to today's video on infinite series, where we will introduce the concepts of a Taylor series and a Maclaurin series, which is actually just a special case of a Taylor series. So we will be covering section 3D of our textbook. I'm sure by now you are sick and tired of the geometric series because it was the only representation that we really knew about, so we tortured it. We did substitutions, we did partial fraction expansions using them, and we did some calculus on them. So luckily today we are going to look at some fresh functions, and we're going to learn how to create power series for them. And this is going to be a general process, so no more geometric series for now. We're going to start afresh and we will see how to create new representations. All right, so here's the setup. We are given a function f of x, and we'll assume that it is infinitely differentiable. That means that you can take as many derivatives as you want, 100, 1,000, 10 million, as many derivatives as possible. So a very good example is going to be e to the x, and this will be our first example in a little bit because, well, everybody knows the derivative of e to the x is just e to the x. So you don't go very far. The first derivative is e to the x, the second derivative is e to the x, the third derivative is e to the x, and so on. So you can keep taking derivatives until the cows come home, as many times as you want. Same thing with cosine and sine. Let's skip over to them. ln of x we already kind of did in the last video when we found the series for negative ln of 1 minus x. So cosine and sine are two other good examples. Derivative of cosine is negative sine. Derivative of sine is cosine. So you're almost literally going back and forth except for a plus or minus sign. And because these are infinitely differentiable, you can compose, let's say, e to the minus 3x. You can differentiate that as many times as you want. Just remember to apply the chain rule. Cosine 2x, you can differentiate that as many times as you want. Just remember the chain rule. And by the product rule, you can take as many derivatives as you want of e to the minus 3x times cosine 2x. Okay. So let's put that aside for now. We will play with them later on. In particular, these three, we're going to play with them. Let's pretend that a very good friend of yours told you, hey, here's a representation. I can assure you it is perfectly correct. And here are the coefficients. The function is exactly equal to a constant, c sub 0, plus c1x minus a, plus c2x minus a squared, plus c3x minus a cubed, and so on. Okay, so you have as many terms as you want in the power series centered at x equals a. Okay, and they assure you, okay, you can plug in any number that you want between, let's say, -1 and +1. It's all good. It will converge. This power series will converge to the function, the value of that function at that particular x. Okay, so we kind of just have to trust your friend, he's a good friend of yours, that this equation is correct. It is valid. Okay, so what are we going to do with that function? Well, we are told that your function is infinitely differentiable. Okay, so more on that in a minute. First thing we'll do is, what happens if we just plug in x equals a? Okay, well, we're going to get a minus a squared. Well, those are all 0. So the only survivor will be c sub 0. Okay, so that means that the 0th coefficient, c sub 0, of this power series representation must be f of a. Okay? All right, so now we will take the derivative of both sides of this equation. F prime of x, c sub 0, that's just a constant, that's going to disappear. So even though we found its value here, it's okay. We'll keep that for later. When we take the derivative, whatever that c sub 0 was, it'll disappear. But we will get c1 times 1, and then by the power rule, 2 times c2 times x minus a, 3 times c3 times x minus a squared, and so on and so forth. Okay, so we all know the power rule. Drop the exponent and decrease the exponent by 1. Okay, so let's scoot on down, and we get the first derivative right there. And then we do the same thing. We will plug in x equals a, and guess what? Again, a minus a squared. These higher powers are all going to be 0, and the sole survivor will be c1. Okay, so we know that c0 is f of a, c1 is f prime of a. Okay, and you might say, oh, okay, so c2 is f double prime a, c3 f triple prime a. Not so fast. Okay, so this is the first derivative. Okay, we get this representation. c0 is gone. We start at c1. We're going to repeat the process. We're going to take the second derivative. Derivative of both sides will give you the second derivative on the left. c1 will disappear. Okay? 2c2, derivative of x minus a is 1. Derivative of this, the 2 will drop down, so you get 6c3x minus a. 3 will drop down, you'll get 12c4x minus a squared, and so on. Power rule. Every time, drop the exponent, decrease the exponent by 1. Okay, so let's see what's going to happen. From here, c1 will disappear. We get 2c2, 3 times 2c3, or 6c3, 4 times 3c4, or 12c4, x minus a squared, and so on, by the power rule. So this time, when we plug in x equals a, 0, 0, the only survivor is 2c2, not just c2. So c2 is 1/2 of the second derivative evaluated at a, right? So we get something a little bit different. All right, so before I scroll down a little bit further, we're going to take the next derivative. We will now have the third derivative at x. 2c2 will disappear, just a constant. And then the derivative of this term is going to be 6c3. X minus a becomes 1. This one, the 2 comes down. You get 4 times 3 times 2, 24 c4 x minus a to the power 1. The 3 will drop down, and you'll get 5 times 4 times 3, 20 times 3, 60 c5 x minus a squared. I hope by now you're starting to see a pattern. 3 times 2, we're going to get 4 times 3 times 2, and then power 1. 5 times 4 times 3, and then that becomes 2. Sounds familiar? 3 times 2 times 1. 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. Those are the factorials. Aha. So the factorials, remember this term started as x minus a to the power 5. Okay? So the 5 will go down, decrease to 4. The 4 will come down, decrease to 3, and so on. The fifth coefficient, c5, will eventually be matched with 5, 4, 3, 2, 1 as we take more derivatives. Okay? So I hope that that is starting to form. Let's take a look at the third derivative. There we are. So we said that the only survivor that's going to survive when we plug in x equals a. Once again, these will all go away, and we are left with 3 times 2, or 6 c3, And so C3 is the third derivative at A, divided by 3 times 2, 6, which is 3 factorial. Okay, the denominator is not 3, but 3 factorial. Okay, so we verify this pattern with the fourth derivative. When we take the derivative of this, constant disappears. We are left with 4, 3, 2. This disappears, becomes 1. We take the derivative, we get 5, 4, 3, 2, C5 x minus a to the power 1, and so on. Okay, so the factorial is definitely appearing right before our very eyes. And when we plug in 0 into the fourth derivative, a into the fourth derivative, that becomes 0. All the higher powers become 0. And we are left with 4 factorial times C4. Now remember, the factorial ends with a times 1, but of course that doesn't affect the value. Therefore, C sub 4 is the fourth derivative at A divided by 4 factorial. Okay, so of course, this pattern will continue. When we get the fifth derivative and plug in x equals A, we will find out that C sub 5 is the fifth derivative at A divided by 5 factorial. Okay, so this tells us exactly who are C0, C1, C2, C3, C4, and C5. So we can plug in those values. Oh, by the way, icing on the cake, we saw that C1 is the first derivative at A, but remember that 1 factorial is simply 1. Okay, so we can write that in the same pattern as the first derivative at A divided by 1 factorial. Okay, what about C sub 0? Well, C sub 0 was just f of A. Okay, so think of that also as f of A over 1. Oh, wait a minute. 0 factorial is 1. How convenient. But what about 0th derivative? Well, what do you mean 0th derivative? Yeah, 0. Do not take a derivative. That's what it means. So keep it as just the original function. Okay? So putting it all together, we get what are called the Taylor and Maclaurin series of a function. Suppose we have a power series representation. Suppose we are given this. You don't know where it came from. You're just reassured. You'll have to trust this person that this equation is valid for all x in some interval I, which is centered at A. Then these coefficients are very special. Each coefficient C sub n has to be the nth derivative at A divided by n factorial. And we agreed that the meaning of 0th derivative is the original function. Okay, so if this power series converges to the function, then that function must be represented by the power series where the coefficients C sub n are nth derivative at A divided by n factorial. And of course, we multiply by x minus A to the power n. All right. So if you expand that out, we will get, as mentioned earlier, f of A plus f prime of A x minus A, second derivative at A divided by 2 factorial x minus A squared, third derivative at A over 3 factorial x minus A cubed, and so on. Okay, so this is called the Taylor series of our function centered at x equals A. The easiest center for any power series, and in particular for Taylor series, is A equals 0. In which case it's called the Maclaurin series of our function. So Taylor was English, Maclaurin was Scottish. And so when A is 0, it makes it shorter because now you have just x minus 0, just x. X, x squared, x cubed, and so on. it's so much nicer to look at. So we have f evaluated at 0, the derivative of your function evaluated at 0 times x, second derivative evaluated at 0 divided by 2 factorial times x squared, and so on. Third derivative at 0 over 3 factorial times x cubed, and so on. Okay, so I promise you, no more geometric series. We are going to play with the exponential function, e to the x. We'll go to our workroom, and we will find its Taylor series. All right, so let's play. We will find the Maclaurin series for e to the x. Okay, so our function, f of x, is e to the power x. In the theorem, we were already told that we had a representation for the function. We are not given a representation for e to the x. However, we can still find its Maclaurin series. Okay, so bear with us for a little bit. All we have to do is, well, first step, plug in 0 into our function, the f of 0. So f of 0 is e to the power 0. Okay, and of course everybody knows that e to the 0 equals 1. Okay, thought I'd make it a little bit bigger. So next we want f prime at 0. Okay, but wait a minute. We mentioned in the introduction that the derivative f prime of x of e to the x is again e to the x. And so f prime at 0 is again going to be e to the 0, which hasn't changed. E to the 0 is still equal to 1. Okay, so I hope you see where this is going. In fact, all derivatives of f of x, which is e to the x, are just e to the x. And so all of these derivatives evaluated at 0 are equal to 1. Second derivative is 1, and the third derivative at 0 is equal to 1, and so on. Okay, so yeah, all of these, that's 1, that is 1 times x, 1 over 2 factorial x squared, and so on. Those numerators are all 1. Okay, and so the Maclaurin series, why did I retype it, for f of x equals e to the x is, let's copy our template over here. We want this, so we will copy that, and we will fill in the numerators with 1s. That's equal to 1. F prime of 0 is 1 times x, so that's just x. And then this is also 1. So that goes away, and we really don't need that times symbol. And then this derivative is also 1, 3 factorial x cubed, and this is 1 over 4 factorial x to the 4th, and so on. Okay, so I hope you're seeing a pattern here. X squared, 2 factorial, x cubed, 3 factorial, x to the 4, 4 factorial, and so on. So we can write this in a compact summation notation. All right, so we already have the symbol above. All of these numerators are simply going to be 1, and we don't really need that times symbol. And if you want to make it look even more compact, we can write it as x to the power n over n factorial. Okay, so we can see forming right here the partial sums of our Maclaurin series. Okay, so in fact, why don't we go to GeoGebra and sketch the graph of e to the x and this partial sum, S4, where we have 5 terms. Let's go to GeoGebra. Okay then, so let us input our e to the x. Ooh, there is our beautiful graph. And then let's paste our S4. Ooh, okay, so there it is. And it's quite different here because, yeah, that's a fourth degree polynomial. And we all know that that is one possible behavior for fourth degree. Eventually, it will go up to infinity on both ends. It might wiggle a little bit inside, but check it out. Zoom in, zoom. Wow, look, yeah, it's kind of up until maybe 1.5 and maybe -1. You can hardly tell them apart, okay? So this gives us some confidence that what we're seeing here is going to converge eventually to e to the x. Would you like to add another term? Let's see if we can make one. Okay, so let's see. Are you going to be nice to me? I'm going to add another term, and we will turn this into 5 factorial x to the power 5. Ooh, check it out. So, of course, fifth degree, it's now going to go to minus infinity on the left. You have a positive coefficient there. And yeah, oh, look, my goodness. Wow. You can barely tell them apart until this is about 2. Okay, so on the left, yeah, -2, before -2, it starts to split off. Okay, so, all right. So our next job now is to convince you that if you take the power series, where you keep going, x to the 6 over 6 factorial, x to the 7 over 7 factorial, and so on, that power series not only will converge, but at every number x, this power series will converge to e to the x. Let's go back to our PDF. All right, so here's how we're going to do it. I hope you remember that when we did the integral test, we said, okay, if your function passes the integral test, if your series passes the integral test, meaning you can integrate the function where it came from 1 to infinity and so on, then we can approximate the exact value of the infinite series, the exact sum, using a partial sum. Remember, we took 10 terms, we took s sub 10, and we said that e sub 10 is between two integrals. Remember that? Integral from 11 to infinity on the left and 10 to infinity on the right. Okay, so in the same way, a Taylor series, this is a Taylor series for our function, has a partial sum, just like what we did in GeoGebra. I can't go on forever, but I can take up to a 5th power or a 6th power. So this now becomes a Taylor polynomial, just like what we saw in GeoGebra. We saw up to the 5th power or the 6th power. Notice that the notation changes a little bit, and this happened in that proof problem that I asked you to do if you were my student, where we write the partial sum, the nth partial sum, using the index k, because n will appear as the upper limit for your partial sum. We use n as the main index for the infinite series, but for the partial sum, n becomes the upper bound. So we need a new index. We can use k, you can use j. I like using k. So the Taylor polynomial is just the sum for k equals 0 to n of the kth derivative at a divided by k factorial times x minus a to the power k. All right, now the error that we obtain by approximating the function with the polynomial is the difference between the function and the Taylor polynomial. Okay, so let's go back to GeoGebra and let's sketch the graph of the error when we subtract the sixth Taylor polynomial from e to the x. All right, and we're back. So here's our function. Here's the partial sum S5. Fortunately, they have names. So the error, let's call it h of x. I don't like using capital E or lowercase e because GeoGebra thinks that e means e, the exponential base. So I'd rather not toy with him. So h of x is the difference, f of x minus g of x. Ooh, okay, there it is. It's in blue. Beautiful. So notice, let's hide these two. Notice that the error is very, very close to 0. Let's say between minus 1.4 and 1.5. Okay, but of course, as x gets bigger, the error gets bigger. All right, so that's not very good. That's not very good, but this is pretty darn good, don't you think? You have to zoom in really close to see that, okay, yeah, it's practically 0. Yeah, so it's pretty good. Between these two numbers, the error is practically 0. Okay, so what we want to show then is that as we take more and more terms, this error is going to go and have limit exactly equal to 0. Now, fortunately for us, Taylor himself gave us an inequality, sort of a formula, except we see the symbol less than or equal to there, because it's an inequality that tells us sort of a maximum possible error that we can get from e sub n of x, the error term en of x. Suppose that your function has at least n plus 1 derivatives on an interval I which is centered at x equals a. Suppose that we can also find a positive number, capital M, such that the absolute value of the n plus 1th derivative of f of x is at most m, for all x such that absolute value of x minus a is less than or equal to d, where d is some positive real number. So remember, this means that x is between a minus d and a plus d. Okay, we have seen that symbol before. So if we can find this number, capital M, Taylor's inequality says that the remainder, e sub n, must satisfy this inequality. Its absolute value cannot be bigger than this m divided by n plus 1 factorial times the absolute value of x minus a to the power n plus 1. Again, for all x such that x minus a in absolute value is less than or equal to d. I will be the first to admit that this is not a very easy inequality to understand. Okay, so first you have to find this capital M so that the n plus first derivative is less than or equal to m, where x is between a minus d and a plus d. And if so, then the error in absolute value is at most this fraction, m over n plus 1 factorial, x minus a to the n plus 1. Okay, so yeah, I'm not going to bother proving this. You can search the internet for a proof. You probably don't want to. We will just accept it for what it is, and we will use it to prove that our Maclaurin series for e to the x is going to converge to e to the x. All right, so let's go back to our exponential function. So we formed the Maclaurin series in our workroom. We have its x to the n over n factorial, and from 0 to infinity. But this was our first example in section 3a, and we used the ratio test to prove that this is absolutely convergent. Now, remember the test for divergence. It said that if a series converges, That's the contrapositive. If the terms of a series do not converge to zero, then the series has to diverge. So the contrapositive, which we mentioned in the proof, is if the series does converge, then the terms of the series must go to zero. So since this series converges, in fact converges absolutely, the terms x to the n over n factorial must converge to zero. And we can see this. If you take 3 to the 5th power over 5 factorial, that's going to be a small number. If you take 3 to the 10th power over 10 factorial, that's even a smaller number. Okay, we're going to need this limit at the end of this example. Okay, so Taylor's inequality says that first of all, your function has to be differentiable n plus 1 times, but e to the x can be differentiated as many times as we want. Okay, so the first sentence is passed. Now we need to find this capital M, but the derivatives are all e to the x. Okay, so we have to think, can we find a capital M so that e to the x is smaller than m in absolute value? Oh wait, e to the x is always positive, so we don't really need that value. For all x such that, our center is 0, so absolute value of x less than or equal to d. Okay, well, that just means that x is between negative d and positive d. Okay, so let's go back to our workroom. By workroom, I meant GeoGebra. Okay, so we're going to restrict x to be between negative d and positive d, right? So I believe we can do this. So for example, if we have minus 1 less than x less than 1, yes, there we go. Our function is restricted between minus 1 and 1. Is there a capital M so that the function is below capital M? Yeah, it's monotonic increasing. So the highest value occurs at e to the power 1 or e. Yeah, e is somewhere there. So what if x is between minus 2 and 2? What if we change the d? So we go from negative 2 to positive 2. Of course. The domain becomes bigger, but is there still a capital M so that our function is below capital M? Yeah, it's below this. Who is that? That's e squared. Okay, so in general, if x is between negative d and positive d, e to the x is going to be below e to the d. Okay. All right, so that is what we just said. If x is between minus d and plus d, then the absolute value of e to the x, which is simply e to the x, will be less than or equal to e to the d, the value of e at the right endpoint of that interval. Okay. So, and we saw that when d equals 2. So now, Taylor's inequality says that the absolute value of the error, e sub n of x, is at most e to the d, that's our capital M, over n plus 1 factorial, absolute value of x to the power n plus 1. Okay, but now we said that the limit as n goes to infinity of x to the n over n plus 1 is 0. Okay, so given any x now, pick a positive number d so that absolute value of x is less than or equal to d, then we have this error being satisfied. But now as we go to infinity, that e to the d does not depend on n. It's just a constant. So therefore, this factor is going to go to n. This factor remains constant. Okay, I'm sorry. This factor is going to go to 0. This is the only part that depends on n. This factor does not depend on n. And we know that this factor goes to 0 because of this limit. Okay, so that's basically the squeeze theorem. If the bigger number goes to 0, then the smaller number goes to 0. And of course, everything here is positive. You have 0 as a lower bound for that value. Okay, so no matter which x you pick, if you take more and more terms in your Taylor polynomial, the error is going to go very, very small, close to zero, which means that we get this beautiful representation for e to the x, which we already had in our workroom, and because this power series is absolutely convergent for all real numbers, this representation works for all real numbers. All right, now if you did your homework on alternating series, there's a problem there about -4 to the n over n factorial. And I said, you know what, wait until you've done all 7 tests before attempting that problem. Because to apply the alternating series test, you have to show that that term goes to 0. Not at all obvious. But now that we know that this is absolutely convergent, then the terms, as we said, must go to 0. So this is a very useful limit. It is not at all obvious that these terms are going to go to 0. But since we know that the series converges, those terms must go to 0. Okay, so we're going to do one more example. We're going to do some trigonometry. We're going to work with sine of x. I'm going to leave cosine of x to you. But also, actually, before we do sine of x, let's take e to the x for a test drive. Okay, so we have the Maclaurin series for e to the x. We will use it to approximate e to the -1/2. All right, so x is going to be -1/2. And so we are going to plug that into our power series. And remember, let me go get the partial sums. Here we go, cut and paste. So these are the first few terms in our power series. We will replace x with -1/2. Now, according to the error formula for alternating series, remember that the error is smaller than, or is at most, the next term not to be added. Okay? So once we add a term which is smaller than this tolerance, I got 5 zeros there, we'll stop. Okay? We'll accept that as an accurate enough approximation. So obviously -1/2 is not going to cut it. So we'll have to add -1/2. And then we will have -1/2 squared. And get down there. -1/2 squared over 2 factorial. I doubt that'll do it. That's not very small yet. Yeah, that's only 0.125. So I want -1/2 cubed over 3 factorial. Let's see, any chance you're small enough? You are -2. No, we need -5. Okay, so there's at least one more term. Maybe 2. Okay, so we will have -1/2 to the 4th power over 4 factorial. How small are you? You are, -3. We're getting there. Okay, so we're going to need at least one more. We will need 5 factorial and -1/2 to the power 5. Okay, are we there yet? Are we there yet? Let's see. 5. Okay, maybe one more. I am willing to bet. Now I'm going to keep my money. Let's see what happens with 6. Let's see. Yeah, there you go. 6 factorial -1/2 to the power 6. Are you small enough? 10, yeah, okay. Let's accept that as small enough. That's enough terms. So add them all together. And what do we get? 0.6065332. Okay. So, yeah, well, we got Maple to help us, of course. Madam Maple, are we close to e to the -1/2? What are we going to get? 0.60653. Okay, so yeah, we got where the first 5 digits are the same. So maybe we should have added one more term, but you get the idea. Okay, our final example. We will look for the Maclaurin series for sine of x, and we will use it to approximate sine of 23 degrees. So I do this in the textbook, but I think it's good to go over it from scratch. I do prove that the error term will also go to 0. So you can check out the proof over there. It's actually easier than for e to the x. Okay, so the Maclaurin series, we need to plug in 0, find the derivative, plug in 0, find the second derivative, plug in 0, divide by 2 factorial, find the third derivative, plug in 0, divide by 3 factorial, and so on. Okay, after we do that, we will use the series to approximate the value of sine at the angle 23 degrees. Okay, so here is our function. So if you plug in 0, f of 0 is sine of 0, and everybody knows that the sine of 0 is 1. Okay, so now we need the first derivative. So let me copy that whole thing except for the 1. Our first derivative is going to be, derivative of sine is cosine. So when you plug in 0 into the first derivative, you are going to get cosine of 0, which is gonna be, oh, I'm sorry, why did I put everybody knows that sine of 0 is 0. Okay, cosine of 0 is 1. It's been a long day. All right, so we will get the second derivative from here. We'll put in the factorials later. All right, so second derivative of our function, cosine becomes, whoops, hang on, here we go. There we go. Cosine becomes negative sine. So the second derivative evaluated at 0 is back to 0. Not 1, but 0. Minus sine of 0 is still 0. What's going on here? Third derivative. So yeah, if you could keep putting slashes over there, it's going to look awkward. So of course, we will use the more intelligent notation. Third derivative at 0. Well, first we need the third derivative at x. So the derivative of negative sine is negative cosine. And so the third derivative evaluated at 0 is negative cosine of 0. Cosine of 0 is 1. So we get negative 1. Okay. So next we need the fourth derivative. Fourth derivative is minus sine times minus 1. Ooh, we're back to sine of x. I'm sure you've seen this before. Okay, we do this all the time in basic calculus. Start with sine, the derivative of sine is cosine, derivative of cosine, negative sine, derivative of negative sine, negative cosine, derivative of negative cosine, back to sine of x. Okay, so therefore, the fourth derivative evaluated at 0 is going to be 0. And of course, once we get there, the pattern repeats itself. This will be the value of the fifth derivative, the sixth derivative, the seventh derivative, and so on. So as a matter of fact, why don't we do that? Okay, so let me make a copy of our computation. I hate it when I do that. I use the wrong sidebar. So this fourth derivative is the same as the original function. The fifth derivative is going to go back to 1. So the fifth derivative evaluated at 0 is going to be 1. The sixth derivative evaluated at 0 is going to be 0 again. And the seventh derivative, evaluated at 0, is going to go back to 1. Minus 1, rather. So that's the pattern that we are going to see. F of 0 is just 0. First derivative at 0 is 1 times x. Second derivative back to 0. That term goes away. Third derivative is now negative 1. And we get 3 factorial x to the power 3. So we keep going. Okay, we also have the fourth, fifth, sixth, and seventh derivative. So let's do that. Let's write this out. And let's go up to 7. Okay, and let's take a look at the pattern. What is the pattern that we are getting? Okay, so the Maclaurin series, let's label it. The Maclaurin series for f of x equals sine x is, okay, so f of 0 we know is 0, right? So why bother writing it? Gone. First derivative is 1, so 1 times x is just x. Second derivative, 0, so that whole term, goodbye. Third derivative, minus 1. So it's not plus, but minus 1 over x, 1 over 3 factorial times x cubed. We don't really need the times. Okay, and as a matter of fact, remember what we did for e to the x? Let's put the x cubed above the 3 factorial as a fraction. Fourth derivative, back to 0, so this goes away, but we're going to do more, okay? So that's 0. Let's do the fifth derivative. We said that it's equal to 1, so this becomes 1 over 5 factorial x to the power 5. And again, let's make it pretty and make x to the 5 over 5 factorial. 6 is going to be 0. 7 is going to be minus 1. So we have minus x to the 7 over 7 factorial. So what I'm going to do is I'm going to copy this and I'm going to turn it into x to the power 7 divided by 7 factorial. All right, you see what's happening? 8, we're going to come back here. Okay, so the fourth derivative is 0. The eighth derivative is also 0. The fifth derivative is 1. What's after that? The ninth derivative is also 1. Okay, so after 7 comes 9, and it's positive 1 over 9 factorial. So we're going to copy this one and make that a 9 over 9 factorial. Okay, so to make the pattern really look good, let's change the x. Let's write x as x over 1, but 1 is the same as 1 factorial. Aha! So now they all look the same. 1 factorial is 1, so x over 1 factorial is simply x. Okay? So of course, this pattern continues to infinity. Okay, so we are going to write this in a beautiful summation notation. And yeah, ratio test, if you take the next term divided by the last term, remember this, you have 7 factorial over 5 factorial, you're going to get 7 and 6 remaining. Okay, so those terms are going to go to 0, right? So I'll leave that as an exercise for you to show that this series that we're about to form in general is going to converge absolutely for all real numbers. So what's the pattern here? 1, 3, 5, 7, 9. Odd numbers, odd integers. But we have plus, minus, plus, minus, plus, minus. Okay, so it's going to be alternating. Okay, so let's start thinking about this. We have this, and it's going to be alternating. So we are going to get an alternating factor. Minus 1 to the something and we want only odd powers, okay? So, and in particular, you want 1, 3, 5, 7, and 9 to appear. If we start at 0, and there's nothing wrong with starting at 0, okay, but odd numbers either look like 2n plus 1 or 2n minus 1, right? But if you start at 0, I believe that you want 2n plus 1, okay? 0 times 2 plus 1 gives you the 1. When n is 1, you get 2 plus 1, 3. Okay, so that's the correct exponent, and that is also what will appear in the factorial. Okay, so 2n plus 1 quantity factorial. Okay, remember those ratio test problems? Here it's going to be very, very important. So now, the alternating part, we start out positive, we start at 0, so I believe we want minus 1 to the n. Okay, when n is 0, you get positive 1. 0 factorial is 1. X to the 1, you'll just get x. All right, so that is the beautiful Maclaurin series for sin of x, and we leave it as an exercise to show that exercise using the ratio test to show that this series is absolutely convergent for all x, all real numbers x. Excellent. So we have follow-up. We said that we will use this series to approximate the sine of 23 degrees. Okay. So it'll be a lot like what we did for e to the minus 1/2. And this time, the power series itself is naturally alternating. Okay? Except our x is 23 degrees. Wait a minute. Whenever we do calculus, that x stands for a real number. So we need to approximate 23 degrees, turn it into radians. What's the conversion factor? 1 degree, or pi radians, is to 180 degrees. Okay, so since we want to cancel the degree, we want to multiply by pi over 180. Okay, the degrees units will go away, leaving us radians. Okay, so that x is, it's about 0.4. Okay, and that's good because 0.4 to the 7th power over 7 factorial, that's not very big now, is it? Okay, so, yeah, let's see. Again, think of the alternating series test. The maximum error that you will get in approximating the exact sum with a partial sum is the next term that you're not going to add. Okay, but what I always say is, well, you already computed that next term, so you might as well toss it in and then stop right there. Call it a day. Okay, so let's see, is x to the 7 over 7 factorial going to be small enough? Or maybe x to the 5 over 5 factorial is already small enough. Let's try that. I'm feeling lucky. So we will replace x with 0.40 something. And how much are you? So divided by, so take that to the 5th power, divide by 120. And oh my goodness, so that is smaller than that tolerance that we had for e to the minus 1/2. Or actually, no, it's about the same size. Okay, so I am fairly confident that if we look at 7 factorial, so yeah, I lost that bet, that should be smaller than the tolerance. Does it have to have 5 zeros? It all depends, you know. Somebody will tell you, your boss will tell you, I will tell you exactly what should the tolerance be. Okay, so that is definitely pretty good. We'll be accurate to 6 decimal places. Okay, so now we will take all the terms up to x to the 7, since we already have that, and we will plug in our x. Okay, So take this and plug it in right there, and this cubed, and this to the 5th, and this to the 7th, and how much is all that worth? It's about 0.39073. Okay, so how good is that? Oh, great Maple. Now, Maple, of course, will want an x which is in radians, so we'll plug that in. And Maple, how much is this? Ooh, check it out. That was 73112. Oh my goodness. So that 7 is off by just a little bit. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's correct to 8 decimal places. All right. So I hope that you enjoyed that video. And next time, we're going to look at some fun things that you can do with Taylor and Maclaurin series. So until then, I hope you enjoy the rest of your day. Bye.